Let's talk about parameterized curves in R3. We introduced parametric equations last week, or we reminded ourselves of parametric equations last week. And so we want to start talking about parametric curves in R3. The goal here is to be able to describe a one-dimensional set in R3. We want to describe a one-dimensional path in R3. So this one-dimensional set will be a curve or a path through 3 dimensions. So this one-dimensional set will be a curve, or we'll say a path in 3 dimensions, like a fly buzzing around the room. It's creating a one-dimensional path in 3 dimensions. When we establish the path, we can only go forwards and backwards along the path. That means there is one dimension. There's forward and -1 times forward, otherwise known as backward. So our goal is to be able to describe a one-dimensional curve or a path in R3. This is just a set of points in R3. The reason I keep pointing out that this is just a set of points in R3 is that eventually, because this is calculus class, we're going to take that set and plug it into some integral. And presumably that integral is going to tell us something that we are interested in. I don't know if interested in is the right word. That might be too strong. That we're going to be forced to do, and at least pretend to be interested in. Eventually, we will be creating an integral that uses this one-dimensional path as the set of things we plug in to the integral. Remember, all we're doing in an integral, the integral part is describing a set of points that we plug into our expression. That's the whole point of this part of the integral over here, this integral symbol. This integral symbol is just telling us what points we're plugging into this expression. Those are the parts, that's how it works. So we're going to have some function, presumably that we'll have to integrate, and it'll be multiplied by some dx, or dt, or dA, or dv. So there's some kind of multiplication that goes with the function and the little delta part that becomes infinitesimally small. These are the parts of integration. These have always been the parts of integration ever since the beginning of integration. Right now, we don't know what this means because we don't have like a surface for what's the area under the surface, or the volume under the surface, or the area under the curve. What are we going to be measuring here? That's the interesting question about what we can use this kind of integral for. But from its mechanical core, integration is just take this expression and evaluate it at all these points. All right. Remember, one of the ways that we describe these parameterized curves is with a vector. We can write a vector form for we can write a position vector with our parametric equations. So I'm going to make a position vector where x is cosine of t in the I direction, sine of t in the j direction, and I'm just going to say plus t in the k direction. We can see what's going on from the top. If we look at this from the top where we can't see what's going on with z, we're just going to create a circle that goes around once. All we're doing now is giving it some height or some depth or length or width, depends on where you stand relative to the curve. But here we're defining a path in 3 dimensions. There's some x direction, some y direction, and some z direction. Let's look at this from different views. So in the top view, we're not going to be able to see what's going on with Z. In the top view, we can't see the Z, so we're just going to see this a circle. That's why I started with this one, because this is the one that we looked at last week when we were reminding ourselves of these parametric equations. This is all we're looking at. From the top view, we can't see what's going on with Z. Z is coming out at us. But we're going to start at this point. Now, if we're thinking in 3 dimensions, this point is going to be 1. Spelled 1 wrong. This point 1, 0 is where we're at when t is equal to 0 and t is equal to z. So this is at 0, 1, 0, 0. Then we're going to continue along this direction, because cosine ti plus sine tj will start off at 1, 0 and go once around counterclockwise. Then the next point is up here, where x is 0, y is 1, and this happens at t equals pi over 2, and that's going to be the z coordinate, which we can't see rising up. Then we're going to continue along, going around the circle, and we're actually coming up as well. Since this is a top view, you can't see me drawing this up, but I assure you, if you could see this in 3 dimensions, it's pretty awesome, because my pen draws right in the air. I'm just kidding. It's drawing flat on the paper, see? So I don't have like a magic pen. But then we get to this point where with x and y, we just see x is -1, y is back down to 0, but here's when z is at pi. So this point is pi units above -1, 0. Pi units above -1, 0. I gotta move the pen towards the camera instead of just directly up. Then we keep going around. We go through the third quadrant. We're still the third quadrant. We're still climbing, so that we still go up, and we're even higher than we were at the start. And now we're at 0, 1, 0, -1, 0 on the x, -1 on the y, and 3 pi over 2 on the z. So I'll go up to 3 pi over 2 and put the dot there. And now this point, 1, 0, 2 pi, that is 2 pi units above 1, 0, 0. So this circle is actually part of a spring going up. It goes once around counterclockwise, but instead of saying flat, it goes up. It climbs up. Let's look at this from a different view. Let's look at this from a side view and see this circle. It's a circle from the top, but let's see this staircase from the side. I want to look at this from, I'm just going to put the x-axis over here. And I'm going to look at what's going on with x and z. We're here, we can't see the y. I can see the x and the z. Y is actually going down into the paper. If we think about our right-hand rule, y is going down into the paper. So in this top view, y is pointing out of the paper. Or sorry, z is pointing up out of the paper. Here on this, in this view, y is pointing down into the paper. So the xz, we're going to see a cosine curve because that's what cosine, that's what x is doing. And I want to plot the point 1, 0, 0. So I'll go 1 on the x, 0 on the y, and 0 on the z. So here's the point 1, 0, 0. Then I want to plot the point 0, 1, pi over 2. So I'll go 0 on the x, 1 on the y, which goes down into the paper, and then pi over 2 on the z. So this spot, I know it looks like I drew it right on top of the paper, but I assure you it is 1 unit down underneath the paper. So here is going to be the point I didn't divide this in threes. It would have taken up too much space. Here is going to be the point 0, 1, pi over 2. We can't see the y, so we're at 0 and pi over 2. Then we're going to continue along. Here is going to be the point -1, 0. So we're back on the front of the paper, but we're up to pi. So there is the point -1, 0, pi. And then back up on the z, 0, -1, 3 pi over 2. And then finally, here is the point 1, 0, 2 pi, 2 pi units above 1, 0, 0. So from the perspective of from looking at this from the negative y-axis, we're going to see cosine. And this, we want to imagine this cosine as a side view of this circle. So here we're going around a circle. So we're going around and then up. So we're getting this spiral moving up. Questions? We have another side view where we're going to draw a sign that goes up and down. We're going to draw a sign going up and down. And we can see that that's going to happen because z is equal to t and y is equal to sine of t. So y is equal to sine of z is kind of one way we could view what's going on here. But we have the side view. I'm going to do this a little bit differently. I'm going to take this x, this one we have here, and I'm going to rotate it this way so that x is coming out, directly out of the paper. So right now, the y is pointed down into the paper. So when I rotate it, y is going to be positive, pointing that way. So x is coming out of the paper. So now we're looking at y and z. We're going to see a sign. So I want to plot the point 1, 0, 0. So I go 1 on the x, which comes straight up, 0 on the y, and 0 on the z. So here is the point 1, 0, 0. Then we're going to move up. The next point is going to be 0, 1, pi over 2. So we go around our circle. We're going to go around our circle to 0, 0 on the x, 1 on the y, and pi over 2 on the z. And we're going to get some practice drawing some sideways sinusoids. So in this third view, x is coming out of the paper. So overall, what we're creating is kind of this spiral that goes once around from a height of 0 to a height of 2 pi. One of the reasons that I broke this down into these 3 ways is because I don't have to draw a 2-dimensional thing. I don't have to try to draw a 3/4 view, even though this is probably like the easiest thing that you can draw in 3/4 views. questions? Comments? Snide remark? The important thing to note here is that we are drawing a one-dimensional thing in three-dimensional space. So we're drawing a one-dimensional curve in three-dimensional space. But once we are on this curve, we have three coordinates. There's an X, a Y, and a Z. We have three coordinates. We have an X, a Y, and a Z. But as far as the path is concerned, there's only forward and backward along the path. When we had a function of two variables, when Z was a function of X and Y, we had an entire surface. So there was 360 degrees of direction, primarily an X direction and a Y direction. That's where we first found our derivatives. And then we looked at any direction. So you have 360 directions that we can go when we're standing on a surface. When we're standing on a curve, we have one direction that we can go. This never works out. I try to do this every single semester and it never works out. I suppose two things that I always think about. I suppose there's like a whole ass art department here at the school. And in 20 years, I haven't taken any art classes for drawing things properly. So that's number one. Number two, I have a whole ass computer right in front of me that could probably produce one of these things and I could spin it around like I'm Tom Cruise in some kind of virtual reality. Or sorry, let me update that one. Tony Stark in some virtual reality where I just have to grab things in midair and fling them around. It might be useful to help see what's going on. It might be useful, but one of the things that one of the reasons that I do things this way is that it doesn't always help to see the thing. It doesn't always help to see the thing. It's important to understand how we're creating a one-dimensional path in three-dimensional space But even if we could do that, one of the things that we're going to be caring about is the direction. Remember, we set this up as a vector. We set these parametric curves up with vectors, because then it would be easy to look at what the tangent is by taking the derivative of each of the components. So if I start thinking about tangents and what direction this is going, I'm not sure that that's really that helpful to actually see the shape of what things are. Because the way that we're going to analyze it is not visually. The way that we interact with this particular curve, it's less about visualizing and more about, here's an equation, how do we manipulate it? There's multiple things that are going on here. There's describing a curve and then working with that description. So there's describing the curve and there's working with that description. So it is helpful in some examples to actually visualize what's going on. But at a certain point, we're going to transform from describing a curve that we observe, let's say, and just start learning to manipulate what we do with the curve. So yes, but that's not complete. Visualizing is helpful, but it's not going to be the ultimate goal. So for example, the question in particular was programming equations in a language. Programming things in a language. Now, if the programming part is useful to you, it helps you analyze things, then 100% that would be a super useful thing to do. If programming, like for me personally, if programming it was going to get in the way and it's going to take several hours just to learn how to do that, then I'm not sure it would be worth it. Does that make sense? One of the reasons that we like Desmos so much is that there's not really a steep learning curve. Just type the thing that you want to see, as long as it's in 2 dimensions, although they have 3-dimensional things coming out. But the reason that it's useful, the reason that Desmos is so useful, is that the learning curve is very flat. It's really easy to just jump in and start guessing how things should work. I find with computer programming languages, this is maybe just a function of my age, but it's not as if I think about if I have to do if I have to write some kind of program to get at the thing that I want to look at, just so I can look at it, that's not going to be useful to me because that's a big block for me personally. For context, the last programming language that I learned was Fortran 77. Does anybody even know what Fortran 77 is? I'll give you a guess what the 77 stands for. So it's not the 77th version. So also, that's on a tangential thing, speaking of tangents. That's also probably why I did not go into applied math, because they're like, oh, welcome to applied math. Possibly the most difficult undergraduate major. I go, ooh, yeah, that sounds cool. I want to be tough. You're going to be talking to computers a lot. So pure math, eh? That sounds good. So we're imagining creating a 1-dimensional path in a 3-dimensional space. One of the things that we're going to be concerned with as we're building these paths, one of the things we want to keep in mind as we move forward is that we're going to be concerned about what direction our path is going. So we're going to be concerned about direction along our path. The direction that we care about is we're going to imagine the roller coaster going through, and we're going to imagine what direction we're headed when we're on the roller coaster at a particular point on the track. And so we are going to be concerned with the tangent. The tangent is going to be described with a vector. We're upgrading our old idea. One of the things that we cared about way back in single variable calculus. What is the slope of the line tangent to a curve at a given point? What is the slope of the line tangent to the curve at a given point? In R3, to describe a line, because we still want the same thing. What is the slope of the line tangent to a curve at a given point? We do have to upgrade some things. Slope is a very particular way of describing direction. Slope is a way of describing direction when we only have x's and y's to worry about. But now we've got x, y, and z. So slope is more complicated in R3. We can't use slope in R3. So first thing we want to notice is that we need something that can stand in for the slope that will work in R3. And so we're going to be describing that as a vector. Vector is going to be our direction. If we just have one vector determines a line, that's what we're interested in. Back in Calc 1, we had such limited options. Slope can be described with one number. Slope can be described with one number, delta y divided by delta x, rise over run. But now I've got change in y, change in x, change in z. Which direction are we pointed? That's why we have vectors now. So our direction is going to be described with a vector. Good news is it's easy to calculate. Just like we saw last week, we just take the derivative of each of the components. So if I want the vector tangent to this curve, that spiral, if I want the vector tangent at any point, derivative cosine is negative sine. Derivative sine is cosine. Derivative of t is equal to 1. So we know what these first two are doing, because if we just looked at cosine ti plus sine tj. We know that makes a circle. And this vector, negative sine ti plus cosine tj, is going to be a vector tangent to the circle in the direction of the circle. Oops. So at any point, we're going to have tangents. Oops. One thing that we want to note is that when we're looking at the derivative, our r prime, our velocity, our tangents at the curve, if we look at the sine and the cosine graph and the sine graph, we see that's not the case. We see this constant 1. Remember that this change is how z is changing with respect to t. So this 1 is the change in z with respect to t. That's how z is changing with respect to t. The graphs that we had were with z against x and z against y. How z is changing with respect to x and y is different than how z is changing with respect to t. Note down here at the bottom, this is where t is equal to 0. And up here at the top, t is equal to 2 pi. And here in the middle, t is equal to pi. So when t increased by pi, z increased by pi. When t increased by pi over 2, z increased by pi over 2. When we look at the slope of the tangent to this curve, if we think of this as the cosine of z, where x equals cosine of z, we've got this vertical tangent here at 1, 0, 0. But that's not the derivative of z with respect to t. That would be the derivative of z with respect to x. So that's one of the things that we want to note. Also note that these 4 tangents that I've drawn on this circle, it looks like they're drawn flat on the page. I assure you they're not drawn flat on the page. They're drawn up at a slope of 1. Any questions? This is what we want to think about. We want to be able to picture one-dimensional curves in 3-dimensional space. And we want to also picture along with that what the tangent looks like, what the tangent vector looks like. And we also want to relate this stuff that we did at the very beginning of calculus, when we want to find the slope of the line tangent to a curve at a given point. We are doing the same thing. We just can't use slope anymore, because slope is change in y with respect to x. And now I have a vector in R3. So I've got to say what's the change in the x direction, what's the change in the y direction, what's the change in the z direction. I've got to describe that with a vector, not just a single number, like we could with the slope. Any questions? Comments? For those of you following along in the book, this is chapter 17 for describing parametric curves, and the integrals that we're headed for are line integrals in 18. Chapter 18 is about line integrals, and it's the setup we're going to have for integrating over one-dimensional sets in R3. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.